So thank you, everybody, for coming today to our Learn workshop. I want to thank all the speakers and everything for putting together these presentations and everything for you. We do have copies of the public notice with the agenda and the speakers' names and stuff on the back table there if you would like some. The presentations that are going to be given today are posted on the Learn website at www.fcc.gov/learn, Learn. We are going to have questions at the end of the presentations, not during, but at the end. If you're sitting here in the audience, we have some note cards on the back table and pens. We ask that you write your questions down. And myself and, raise your hand over there, to the FCC staff, just hold them up in the air. We'll come collect them from you and get them up front. People that are watching remotely, if you're watching on WebEx, the audio would be on www.fcc.gov/live. And if you're watching either via WebEx or for the live stream, you can submit questions by sending an email to livequestions@fcc.gov. Due to time constraints and the amount of questions we get, we'll try to get to as many as possible. And now to get us started, I'd like to introduce Julie Knapp, who is the Chief of the Office of Engineering and Technology here at the FCC.
Thanks, Cecilia. Thanks for all the work, too, in helping getting this organized. So welcome to this afternoon's workshop on interservice interference. I would just make one edit to that. It should be preventing interservice interference. We've got a great panel that I think is going to dive into this in depth, but I thought maybe I'd just give you an example, very hypothetical, not realistic, but just to help you understand what this is all about. So it's a voluntary incentive auction. So suppose the entire nation converged on a particular amount of spectrum that was going to be recovered and repurposed, but there was just one market that where 10 megahertz of spectrum less was recovered. Well, then in that market you would have TV operating, and you've got other markets where you'd have wireless service operating. So another hypothetical. I think everybody would take as a given fact that you can't have wireless and television service operating in the same market. They would interfere with each other. So there has to be some separation. So what this is about is, how do you determine what the separation would need to be? And what would the impact be on the availability of spectrum in the surrounding markets and so forth? So we had folks had submitted comments into the record on their thoughts on how that problem should be addressed. The team in OET working with the Wireless Bureau thought about this some and came up with a methodology that tries to tailor how we would control this interference based on the specific characteristics in each case, the characteristics of the television stations and the characteristics of wireless broadband. And so the team here this afternoon is going to walk you through the methodology. It is a little deep on the technical side, and we'd be happy to take questions at the end of it. And I will turn it over to Matthew Hussey, who's going to MC this session. Thanks.
Okay. Okay, we can pull the slides up. So I know people don't want to be looking at my ugly mug. So, okay, there we go. Oh, where's there? Yeah, well, I want to first thank all of you for being here. I really appreciate it. As Julie said, we are going to be delving in some pretty complex technical issues, so don't let the simple agenda fool you. And for the engineers in the room, this should be very interesting since it's such a complex and technical issue to discuss. But for the non-technical people, we just hope you don't fall asleep during the presentation. But what I'll do is just first go into a little bit of overview of the public notice itself, talk about how interservice interference and market variation relate. Then I'll turn it over to Bob Weller, who will go into market variation in much more detail. and kind of talk about the differences between a separation distance variation and the more granular approach that we are presenting today. Then two OET engineers, Martin Dozcat, sorry for messing that up, and Barbara Pavone will go into a lot more detail about the methodology itself, some of the assumptions and parameters that were used in developing, as well as the analysis that was done. And then we'll have Brett Tarnitzer, who spoke earlier today, kind of talk about how such methodology might be implemented into the auction mechanics, incentive auction mechanics. And then we'll have open it up for a Q&A. But as Julie kind of alluded to, the overall goal of the incentive auction is to clear a uniform amount of spectrum nationwide. But because the voluntary nature of the reverse auction, we could most likely have different amounts of broadcasters participating in different markets. And also the cross-border issues that we have to deal with in regards to Canada and Mexico TV operations may cause variations in the amount of spectrum that is ultimately cleared. And we don't really want to go down to a lowest common denominator, because that will artificially suppress the amount of spectrum that can be repurposed for wireless broadband. And also, by going to that lowest common denominator and not allowing market variation, we would also actually possibly limit the number of broadcasters that are wanting to willingly participate in the reverse auction. So, with that in mind, when allowing market variation, you're obviously going to have co-channel operations, adjacent channel operations of both the new wireless service and the existing broadcast service, and that could cause inter-service interference. And so we want to properly minimize and prevent that if possible. And so a group of engineers, FCC engineers, kind of took that as well as three overarching goals in trying to determine how to properly minimize inter-service interference. And the first one was obviously, first and foremost, to protect broadcast services and their viewers from harmful interference. The second one is to ensure that wireless bidders are informed about the licenses that they are bidding on. And then finally, which has been kind of a common theme in any spectrum discussion, is the efficient use and utilization of spectrum resources. And Julie also kind of commented that there were several commenters that addressed the issue of inter-service interference, or at least raised a concern about it. Several proposals to address inter-service interference were presented, and one of the most common themes was a predefined separation distance. And that was ranged, as you can see on the slides, anywhere from 100 kilometers to 500 kilometers. And there wasn't a significant amount of technical detail to support some of those ranges. So we really kind of looked at what we could do to, instead of taking this, kind of one size fits all, to use more of a case-by-case methodology or approach that would actually take into account real-world characteristics, such as the operational parameters of the TV services as well as the wireless systems, also terrain variability, which will exist from coast to coast. So taking into account the three overarching goals and these issues, we believe we developed a methodology that really provides greater granularity and therefore greater accuracy in predicting where harmful interference may occur, but also provide greater flexibility so that we don't unduly leave large amounts of spectrum on the table that couldn't be used in certain geographical areas by wireless providers, while at the same time protecting broadcast viewership as well. And so with that, we did release a public notice end of last month, January 29th, and comments are due February 28th, next Friday, if I'm not mistaken. And it really is, again, not to try to oversimplify it, but it is, the PN in this workshop are really to build the record on an alternative methodology to minimize inter-service interference. We're not making any proposals because that would have to be decided by the commissioners, the chairman and the commissioners. But again, we are just simply presenting an alternative to some of the ones that were, submitted in the public comment period. And it should be noted that there are a lot of outstanding policy issues related to this. The PN kind of touched on some of them, just kind of lightly scratched the surface on it. But this workshop itself will primarily deal with the technical issues related to it, and we do expect that any policy-related issues will be addressed in the future, and that there will be ample opportunity for stakeholders to weigh in at the appropriate time in regards to those. But if you had a chance to review the public notice and the PN, you'll kind of see kind of the issues that we really kind of teed up to request solicit comments on. But it's really about the methodology, and if commenters believe that this is a more accurate approach, or if there are alternatives that could be used that have not yet been vocalized in regards to how we can minimize inter-service interference. We also go into requesting comments on a whole host of issues that relate to the operational parameters and propagation models that we use in our analysis in the development of the methodology itself. And we also kind of ask about the appropriateness of using a uniform distribution of wireless base stations in one of the interference scenarios, as well as the use of proxy channels for our analysis, and then finally, what's the last one? Okay, and using a threshold. The appropriateness of having an interference threshold into DTV service, given real world scenarios that exist. And so with that, I'll turn it over to Bob Weller that'll talk about market variation in more detail.
Thanks, Matthew. Slides somewhere. There we go. My name is Bob Weller. I'm Chief of Technical Analysis at the Office of Engineering and Technology. This works. There are so many unknowns in the incentive auction. I think we need to embrace facts, and I hope this workshop will help elucidate at least one of the more challenging aspects of the incentive auction, and that is dealing with the market variation problem. So first of all, what is it? Basically, market variation is when some frequencies are used both by television and by wireless at the same time. Obviously, to avoid inter-service interference, the two services have to be geographically separated. And one question that arises is, by how far do they have to be geographically separated? Also, in an auction setting, which is why we're all here, market variation creates complications in terms of defining license areas because radio waves don't respect license area borders, and they can cause interference over fairly great distances, in particular in neighboring license areas. It's not practical to eliminate all interference due to market variation, so one must ask how much interference can be allowed before a wireless market is effectively impaired. And the work we're doing in OET is intended to calculate the degree of impairment based on some typical assumptions, but we also realize that technology can improve and will continue to improve on that typical case. This is a really important slide. So we made it into a poster so you can look at it for the entire workshop. It illustrates the 4 potential interference cases that can exist due to market variation. Martin and Barbara will go into them in some detail. Another question that arises is where in the spectrum should we try and place unavoidable variation? While the FCC has not yet made any decisions on band plans, we could place impairments in the uplink spectrum. Doing so assures nationwide availability of downlink spectrum, allowing for interoperability and low-cost consumer devices. There are some very good reasons for doing that. Here's an illustration of how impairing the uplink spectrum might look. There's an amount of spectrum cleared, ideally nationwide, but let's just say in most markets. That's called the clearing target. Impairments can arise for a number of reasons. In some markets, there may be insufficient broadcaster participation to make that clearing target. So we have to leave one TV station on the air in spectrum that's otherwise repurposed for wireless, and that's shown in yellow here. We might put that station in the uplink spectrum, as shown here. And of course, we'll also need a guard band to protect TV receivers. And similarly, we can add a second TV station or a third TV station, and we still keep the downlink spectrum uniform on a nationwide basis, and we're impairing only the uplink spectrum where filtering is a lot more feasible, we think. So we just looked at where in the spectrum we can create or might create impairments. We also need to identify the area over which that spectrum might be considered impaired. An obvious way to do this is to work out the maximum distance at which interference might occur and just preclude wireless operation within a circle having that radius, and that's what's shown in this slide. This approach has the disadvantage that an impairment in a single market, like New York is the example I'm using here, can preclude wireless operation in many other markets, like Boston and Washington, D.C., which are quite a ways from New York. In any case, there are some terrain features that may make such a large distance unnecessary. And that's why we're considering using a more granular approach. So by doing a large number of interference calculations on a point-by-point basis, we may be able to reduce the preclusion distance in some directions. And also, as shown here, protecting every single location can lead to much larger preclusion distances than would otherwise be necessary. So if you look at the distance necessary to eliminate interference to 100% of the points, it's a much larger number than if you consider 99% of the points. And these are points by area, but they're irrespective of whether there's population in them or not. In the lower left-hand corner of this slide, you can see that the protection requirements for adjacent channel interference, which we're also considering, are much less restrictive than for the co-channel case, which is the main part of the slide. So I just want to emphasize that the purpose of market variation is not to allow recovery of every last megahertz in every single market. Rather, the purpose is to prevent, as Julie and Matthew said, prevent having the nationwide clearing target limited to what can be cleared in the most constrained market. So last summer, we described in a January public notice how we were able to take very granular DTV coverage and interference information from our TV study software and use it to generate constraint files. And those constraint files can be very, very rapidly applied during the auction. And that's what this morning's workshop was all about. It occurred to us that a similar approach could be used to deal with the problem of market variability. So the methodology we're presenting is complex, and it generates a very large amount of data, but it's not incomprehensible and it's not impossible, and I think there is a great deal of value to this approach. So the next speaker is Martin Dosgat from my branch, and everybody take a deep breath because it's going to be a very deep dive.
Thanks, Bob. So I'm going to present some overview slides where I'll explain how we use both transmitter and receiver performance standards to derive field strength thresholds to protect both DTV and wireless services in the event of market variation. So briefly, here's a recap on the cases that Bob suggested are very important in this whole process. For case one, which involves DTV transmitters and wireless base station receivers, we have a similar propagation path as DTV, except the receive antenna height for base stations is typically higher above the ground than, say, a rooftop TV antenna. For case two, which involves DTV transmitters and wireless user equipment receivers, we have typically lower receive heights, and so we expect that there will be some significant losses along the path due to ground clutter, which could be from obstructions such as vegetation or buildings along the way. We'll go further into details on clutter later on in the presentation. For case three, which involves wireless base station transmitters and DTV receivers, we use the clutter losses in OET Bulletin 73, which provides for some broadcast reception situations. We may not need to consider case 4, which involves wireless user equipment transmitters and DTV receivers, because the distances involved are likely less than a few kilometers, and so therefore might be subsumed by some of the other cases. As far as transmitters, we know where they are for DTV and how they operate through the FCC's Consolidated Database System, or CDBS. However, since wireless services are typically licensed by geographic area, a transmitter could be operating from anywhere in that license area. We'll go into detail about how both DTV and wireless transmitters on the next few slides. For DTV, we pick the values right out of CDBS and OET Bulletin 69 for the emission bandwidth, the effective radiated power, antenna characteristics, geographic coordinates, and transmitter height. For wireless, we place hypothetical base stations 10 kilometers apart at 30 meters antenna height above average terrain, or HAAT. HAAT considers in part the intervening terrain, but it's not a perfect solution. This uniform approach might miss some pockets of terrain or population, but it might be just as inaccurate in some instances to use actual site location data during the auction, because even given present site information, we aren't certain how base stations will be distributed in the future. To offset the possibility of error in our uniform distribution approach, we've conservatively assumed the largest transmitter we found to be available on the market and doubled it to account for the possibility of MIMO. And we assumed an antenna azimuth pattern to be omnidirectional. We also assumed typical values for the line loss as well as the gain, height, and elevation pattern of the transmit antenna, and we chose to ignore any reductions in effective radiated power due to network power control. Additionally, we so far have considered the possibility of conservatively making impairment decisions across larger portions of license areas rather than just on a site-by-site basis, such as county-wide or by county. User equipment transmission would be applicable to case 4, and so wouldn't necessarily need to be considered if, as mentioned earlier, the associated distances for this case would be subsumed by the distances for the other cases. However, in the event that we find that these parameters may be needed, we've derived them in our methodology in a similar format as for the base stations. Again, we would conservatively assume no power control as well as no losses due to the user's body for the user equipment. Just as we did with the transmitters, we'll go into the details about what we assumed for DTV and wireless receiver performance on the next few slides. For DTV, we assumed the DTV planning factors for UHF in the far right column of this table. Most of this information can be found verbatim in OET Bulletin 69. Using these planning factors, a threshold received signal power level of around minus 84 dBm for successful reception equates to a minimum field strength of around 41 dB microvolts per meter. This is not new information. These factors are already in a number of FCC publications, but they provide the basis for how LTE reception thresholds are analogously derived on the next two slides. Similar to how we derived the DTV planning factors, we also derived thresholds for reception at the wireless base station, but with a few notable differences. Signal to interference plus noise ratio, or SINR, isn't explicitly addressed for wireless like it is for DTV for two reasons. Number one, without site-specific information, we won't be able to predict a desired wireless signal strength to compare to the predicted undesired interfering DTV signal strength in a license area. And number two, technical analyses we've seen on LTE performance have explored a wider range of SINR values. Also, in contrast to DTV, where communication is often over the radio horizon, we add an antenna discrimination factor in this table, shown in the third row there, since wireless base station antennas aren't typically pointed at the radio horizon. The resulting antenna gain is based on a representative average of panel antennas in both land mobile frequency bands in the 400 to 500 megahertz range, as well as in the lower 700 megahertz wireless band. And we consider, in the next to last row, the on-tune rejection, since wireless receiver tuned to a particular block will at a maximum be on channel with 5 out of the 6 megahertz in any DTV channel. Wireless user equipment assumptions have similarly been derived as for the base station, with the major differences from base station parameters being antenna gain, reference sensitivity, and line loss. All of those previous tables have been related to co-channel operation, but what happens when 5 megahertz wireless blocks and 6 megahertz TV channels are misaligned? Off-frequency rejection accounts for this by looking at the combined effect of both transmit and receive filters into adjacent channels. Another technical term for this is adjacent channel interference ratio, which is the sum of the unwanted emission power from one transmitter and a receiver's ability to reject that unwanted power or be selective on its adjacent channel. We assume that the interferer appears noise-like to the victim receiver. The assumption of interferers being noise-like into DTV has been substantiated by measurements conducted by the FCC lab. In those measurement results, both 8VSB DTV and DVB-H, which is an OFDM signal used for broadcast with properties similar to LTE, were each compared to Gaussian white noise of varying bandwidths, but with the same average in-channel power in terms of a DTV receiver's interference susceptibility from those sources. The results show that most interference events in the DTV receiver were measured where these interfering signals differed by no more than approximately a decibel. We interpret these minor variations to mean that there's no practical difference between the effects these interfering signals may have on DTV receivers, and thus we consider them to be equivalent for the purposes of our methodology. Here are our transmitter and receiver assumptions for DTV. The top is the FCC emissions mask for full power DTV, and the bottom shows the first adjacent channel rejection capability of the receiver per the ATSCA 74 standard. And here are our assumptions for the transmitter and receiver for LTE, for both base station and user equipment. The top is the standard 43 plus 10 log P emission for many wireless services, and the bottom shows adjacent channel selectivity and blocking for each receiver per the 3GPP specs. I apologize that it's pretty small. For both DTV and wireless, you might notice that the steep roll-off at the channel edge is uncharacteristic of real-world performance. We note that actual filter roll-off begins well before the channel edge, before dropping off into adjacent channel values, and may only affect the first 100 kilohertz or so beyond that channel edge before dropping off. The effect of this roll-off is reduced when averaged over 1 megahertz blocks, as we've done for our methodology. Moreover, we find it reasonable to assume that receivers will be able to meet or exceed the minimum specs set by the standards bodies. To derive these OFR values, we used NTIA's MSAM program, starting with the co-channel values presented previously. MSAM, which stands for Microcomputer Spectrum Analysis Models, is a suite of tools used for spectrum management. We used their FDR, or frequency-dependent rejection tool, for our derivation using the transmit and receive filter assumptions presented on the two previous slides. An example follows on the next slide. And hopefully it plays, yes. So in this animation, this video, you'll see where the DTV station starts off co-channel and moves along to the first co-channel to the one wireless block, which is shown initially in blue. It'll repeat. And then the second adjacent channel in gray. Right there. And as it moves along, as the arrows move along the bottom of the screen, they relate to the relationships that we've derived in our tables. The overlap starts at 5 megahertz and goes all the way down to minus 5 megahertz. We haven't gone past minus 5 because of the Commission's proposal in the NPRM, which suggests that the 6 megahertz of spectrum separation may be sufficient to protect DTV from wireless. Here are the resulting OFR values that we calculated. All of these values are straight from our table in the technical appendix, so I won't go into too much detail here. However, note that for co-channel, where overlap is 5, OFR is always 0. Also, as mentioned previously, the adjacent channel emissions in the first 100 kilohertz or so affect the results over the first 1 megahertz immediately adjacent to the channel edge, where the overlap is 0. Beyond 1 megahertz, we get numbers that seem to be more characteristic of expected first adjacent channel performance. Applying these OFR values in 1 megahertz increments, we get these minimum field strength thresholds for wireless on the top and the minimum DDU ratio thresholds for DTV on the bottom. Again, these are field strength thresholds for wireless reception because we don't know the signal strength of the desired wireless signal, and these are DDU ratio thresholds for DTV because we are able to predict both desired and undesired signal strength for that case. As you see here, the minimum field strength thresholds for wireless get to be increasingly positive with a reduction in overlap due to the reduced sensitivity to interference in the adjacent channel. Similarly, the minimum DDU ratio thresholds get to be more negative for the same reason. And Barbara Pavone's going to come up and talk a little bit about clutter among some other topics. Thanks.
Thanks, Martin. So I'll finish up with clutter on the parameters, and then I'm going to go in to talk a little bit about TV study and how you can apply this methodology using TV study. So I could have the slides right. The OET methodology suggests that clutter losses should be applied in 3 of the 4 interference cases. This slide illustrates the 4 interference cases and our clutter assumptions for the interference paths. For the interference paths between the TV transmitter and the base station receiver, that's case 1, we do not apply clutter factors to the path. However, we do apply clutter factors for all other interference paths. In case 2, this means the path between the TV transmitter and the user equipment. And for case 3 and 4, this means the interference path between the base station or the user equipment and the TV receiver. Note that we do not apply clutter to the desired path between the TV transmitter and the TV receiver. So, derivation of the clutter factors. To develop the clutter factors for the OET methodology, we started with the accepted clutter factors in OET Bulletin number 73, which are specified for TV receivers at a height of 30 feet. OET's methodology applies these clutter factors for the cases between the base station transmitter at 30 meters and the TV receiver. To adjust clutter factors of OET 73 for paths involving the wireless user equipment, we applied the height gain equations found in ITU recommendation P452 and normalized the results to OET 73 numbers. This means we assumed clutter heights of 10 meters and evaluated the height gain difference between a receiver at 10 meter and one at 1.5 meters. We then applied the difference to the OET 73 numbers to find the suggested numbers shown on this slide. The values in this slide can also be found in the public notice in tables 14 and 15. The land use database that's distributed with TV Study uses 16 categories of land cover. These 16 categories are mapped in the TV Study GUI to 10 categories as shown on this slide and in table 13 of the public notice. So next I'm going to talk a little bit about how to use TV Study to apply this methodology. I'll note, in case you don't know, and you probably all do, that TV Study is available for download at the Learn website. It comes with the code and all the associated databases. So there's 5 basic analysis steps we go through. I'm going to go into a lot more detail in the following slides, so I won't spend much time here. But in general, I'm going to talk about creating the XML scenarios and creating the study parameters so that it runs according to the methodology. The first step we do is we create the baseline noise-limited service contours. We need the baseline contours to determine the protected areas for the TV stations. And as will be shown, these contours are instrumental when post-processing the results to protect the TV station area. Now I'll talk a little bit about creating that television to wireless scenario. For cases 1 and 2, we want to create a scenario that includes all the DTV stations that will be considered. To use this methodology, pre-auction, when the final market variation situation is unknown, we would use a single proxy channel to pre-compute the interference results. In the TV study GUI, you can only set replication for one station at a time. Therefore, an easy way to create the scenario for cases 1 and 2 is to create the scenario in TV study and export it to XML. Then, using a simple text editor, you can add the replicate element to the XML scenario and re-import it. Hopefully this slide is visible. So now I'm going to talk a little bit about setting up the study in TV study for cases 1 and 2. In the case of interference from TV to wireless, the OET methodology uses field strength thresholds for interference, as Martin just said. This means we need to calculate the field strength from TV out to at least 17.3 dBu for case 1 or 33.8 dBu for case 2. However, TV study will only calculate field strength from a TV station within its noise-limited contour. Thus, for cases 1 and 2, we need to specify the threshold for this contour at much lower field strength levels than would normally be the case. For this example, we've used 0 dBu and an F5010 curve to show the contour that would be created if we extended it out for this case 1 and 2 analysis. Then the parameters in TV study that are set up are shown on this slide. The ones shown on this slide deviate from our default settings. Otherwise, we use the default settings that aren't shown on the slide. Clutter is turned on, but set to 0 loss for all categories. This means that the path loss will be calculated without clutter, but the information on the clutter category will be provided in the output files. This allows us the maximum flexibility in adjusting for clutter factors without having to rerun the whole entire TV study analysis, which sometimes can take a while. Also of note on this slide is the use of the Longley-Rice propagation statistics set to median situations for 50% of the locations and 50% of the time. Historically, when evaluating interference, we have used the F5010 for interference path. However, in the case of interference from DTV to wireless, we recognize that modern wireless systems may be more capable of rejecting interference at a higher rate of success, and also may be more robust in rejecting interference signals at higher rates of probability than conventional systems. So when we get the detailed output file, we start to process the data. And so this now talks about processing the data of the analysis results from TV to wireless. The detailed tvstudy.cell file contains detailed information on a grid cell by grid cell basis. In OET's post-processing of the data, we simply flatten the output file to a single line for each facility in each grid point. Because we turned on clutter but set all the factors to 0, we need to adjust the reported field strength for case 2 results based on the clutter category for that point. Another output file that comes out when you run the TV study analysis is the points.csv file. This file is important because it provides a single point key information that specifies a grid point without having to specify specifically the latitude, longitude, and the country key for that grid point. So we use that in post-processing the data. So what do we do with the output? So once we've flattened the detailed tvstudy.cell data, there are 2 primary features we need to look for when evaluating the results of the detailed data. First, we make note if the grid cell is inside the protected contour of the facility. Regardless of the results of the comparison of field strength against the interference threshold, we want to know when the location of the grid cell falls inside the protected contour of the TV station. So we make a note of that for every grid cell. Next, we look for the interference points. We mark all the grid points that exceed the interference threshold as determined by the spectral overlap. In this example, I'm showing the spectral overlap for +5 and -5 megahertz with TV in the downlink. And this is the same example with TV in the uplink for the +5 megahertz overlap. You notice the difference in size of interference is caused by the fact that in this example, in this case, the case 1 example, you would have a higher base station receiver and you would have different sensitivity characteristics, receiver thresholds. And then to finish up TV to wireless, this is the information we provide for constraint generation. What we provide is a line-by-line file that contains, for every grid cell point, information on which grid cells are within a facility contour and which ones cause interference from that facility to the thresholds of the wireless systems nearby. Now I'll talk a little bit about the other direction. So that, in our example, is cases 3 and 4. The scenarios for cases 3 and 4 are a little more difficult to create. We need to collect 2 pieces of input information before creating the scenario. You first need the location of your wireless system transmitters. In the case where these are unknown, OET uses a uniform 10-kilometer spacing of transmitter locations. And second, you need to identify all the CDBS stations within 500 kilometers of your wireless transmitter locations. With this information, this looks like a bit of an art chart, so nobody can probably read that. With this information, you can create the XML scenario for these cases. Using the information provided in Appendix I of the TV Study Manual, we write an XML scenario listing the data for the wireless sites and the CDBS sites. All wireless sites are listed as undesired and unlocked, while CDBS sites are listed as desired and locked. What this means, the CDBS sites are considered always the victims, and the hypothetical base stations are considered the interfering sites. By keeping the CDBS sites locked, we need to provide much less information in the XML scenario, and it reads the data directly from the CDBS database when it's imported. The information on all the elements of the XML scenario can be found in the TV Study Manual. However, I will note here that latitude and longitude values must be in NAD27 format. Also, by setting the height above mean sea level to -999, we ask TV Study to derive this value. And last, we use the generic TV Study transmit antenna pattern for our hypothetical sites. And so these are the study parameters that are different from the default. For cases 3 and 4, actually, most of the study setting parameters are in the default template, and we don't deviate from them. Where we do deviate, we turn on the option to mirror the generic transmit antenna patterns. We turn on clutter, but again set all values to 0. We ignore the Longley Roast error codes so that all path loss that returned is used to determine the signal strength at that point, and set the minimum transmitter height for case 4 to 1.5 meters. And so when TV Study does the calculations, and again, this can be quite a bit of data, it takes and does a calculation from every one of the hypothetical transmit points to every single 2x2 kilometer grid within the contour of every single facility we're studying. So you can see how you get quite a bit of data out of this analysis. Again, we get out the detailed tvstudy.cell file out of the TV Study run. And we take it, and this one will have lines for desired signal strength, undesired signal strength, and DDU ratios. We apply clutter to the U path and then calculate the final DDU ratio in this case. Similar to how we approach the post-processing of the data in the case of TV to wireless interference, we look for all the wireless transmitter points that fall within the protected contour of the TV station. We want to make note of all these points. We also make note of the base station points that cause interference based on the DDU thresholds. In the public notice, we ask if we should consider grouping the results of the wireless interference to TV analysis by some larger boundary. This picture shows the results of the study where the county boundaries are used to group the results. Those gray counties contain hypothetical base stations that are inside the protected contour or contain at least one of many, but just one that causes interference inside the contour. So I've grayed out the county boundaries there. And then this is an example of the constraint file, the data that we provide to the constraint generation team to process. Again, we list the grid cell where the interference occurred, the information on whether or not the base station was inside or outside the county, and a boundary file ID, which if it's a county, the FIPS code, if it's not a county, if it's some other, it could be an EA even, which would take out large areas all at once for one base station, but you could set the boundary whatever it needs to be. And we provide that information to the constraint generation team. So now I'll turn it over to Brett.
I don't have a lot to say, so I'm going to just stay sitting down to do it. But I guess I'm often in charge of putting the pieces together and saying how this all might work with the auction. So while this is really about the methodology for determining separations, this data could allow us to map the impact of TV station assignment on wireless operations when determining what's offered in the forward auction. So when we know the participants in the auction and maybe more importantly, the non-participants who from the outset will need to be assigned a TV channel, we could use some approach, perhaps optimization, to determine if and where we may need to impair wireless markets in order to meet a given clearing target. So, these determinations, of course, will depend on broadcaster participation, but also on the band plan that's chosen and the geographic licensing areas that are ultimately chosen by the Commission for use here. So this is just the first step in the prevention of inter-service interference as it relates to the auction, and we would anticipate future talk about how we can use this information to actually determine the wireless markets that will be offered in the auction. And I think that's about all I can say about that right now. So that's all. So that's all I will say about that right now. Though we're happy to answer questions about it. Yeah. So, and if people here have questions, they can write them on the little cards and raise your hands. Somebody will run around and grab them.
And I guess I'll start off with the first question, which we've had come up in several of our discussions, is about the complexity of this approach. And certainly, there's been a common theme from stakeholders, from Congress, about keeping the incentive auction simple. And so there's, I guess, some may say, well, is this going to be add another layer of complexity? And while it is more complex than, say, the predefined separation distance, we believe it also provides greater accuracy in the predictive modeling of where harmful interference will occur. So, I mean, like I said in the beginning, there's always going to be trade-offs, and we believe certainly that the benefits that are derived from this more precise methodology would outweigh the complexity that it would add. And and it's also because of how we're already using TV study to determine, TV to TV interference. This is just another building block, if you will, or I guess I should say it complements that extensive analysis already. And one of I think the underlying goals of the agency itself is to always work to improve its internal processes, to make them more precise, to improve the accuracy, at the benefit of not only stakeholders but the public in general. And we believe that certainly is the constant theme that we're holding in presenting this methodology. Okay, there. And this may, for Martin, if he may want to answer this, or Brett. There was a question about the emission mask on slide 32. I don't know if we can pull that up. But it was in regards to what is the measurement bandwidth for the wireless emission mask indicated as negative 43 plus 10 log p watts. The commenter or the questioner said, I understand that p watts is the total power of the mobile in watts, so the out of a band emissions is usually negative 13 dBY or dBMY.
Yeah, well, we did it per the rules, but we adjusted it to a 1 megahertz bandwidth. So that's probably the difference.
Well, and this may be for Gary or Julie, but there have been a couple filings requesting an extension on the comment filing deadline, which is February 28th. And I don't know if Julie or Gary would like to address that.
So I think all we can say at this point is they're being considered.
So I have a question here. We've described the goals of the proposed methodology as minimizing interference and maximizing spectral efficiency. Well, which is it? And it's both. There's clearly a balance to be achieved here. And one of the things that we sought comment in the public notice and the appendix on is how much interference is too much, and how should we be defining an impaired market? So I think I have some ideas, and I'm sure everybody in the room has some ideas about where those points should be set. But these are both goals of the methodology.
We have another question emailed. If, as part of the incentive auction, there are TV stations moving from the UHF to the VHF channel 6, what are the implications for and what will be the impact on non-commercial radio operations that are already existing and adjacent to VHF TV channel 6? This doesn't apply. So the answer is this does not apply. Sure.
How do we turn this on?
It's
on?
Yeah.
Why do you assume that a wireless base station listening for a faint user device signal may be better at rejecting the undesired signal than typical systems, i.e. why F5050 instead of F5010? So, as I said, we used F5050 in our analysis because we presume that the wireless systems may be a little bit better at rejecting signals, but we're asking for comment on this as well. So if that's something that we strongly feel against, we should definitely hear your comments on that. I have a second question. Go ahead.
Let me just add to that. LTE system include technological features that don't exist in the DTV world, like MIMO, for instance. And inherently, you get some interference rejection benefit using MIMO. There's also other benefits that are associated with LTE because there are fallback modulation constellations and more sophisticated processing. I mean, the bottom line here is we think that, or it may well be, that LTE systems are simply, including user equipment, are simply more robust to the presence of interference and can tolerate interference not only at higher levels, but can tolerate interference that occurs more frequently in a statistical sense.
All right. The second question I have is, what is the rationale for applying OET73 clutter to the wireless base station? OET73 applies clutter to DTV signal. Why is it only applied to the interfering wireless signals? So when we looked at interference to the TV, we wanted to try and follow as closely as possible the OET69 methodology. So in that methodology, the desired signal doesn't have clutter on it at all. However, the path between the TV to the TV receiver is a much straight, direct path than from what we assumed, a 30-meter height, about a 100-meter base station, to the TV receiver at 10 meters. So that's why we chose that difference in the path adjustments.
Here's a question. Will external interference impacts be considered in the auction in some way? And external interference comes from sources outside of the broadcasters and wireless operators.
Well, I'll go off script here and say Julie's covering his ears. And say that this goes to the things like the DTV planning factors, and we're not at liberty to make any changes to those. But if you look historically at what's been included in other planning factors, yes, there are things that account for or try and account for local sources of electrical interference and those sorts of things. But we're not proposing to account for those here.
Okay. And here's another question. Did the consideration of overlap interference into DTV consider actual 8-VSB demodulation, actual tuner nonlinearities, or did it simply calculate power ratios?
Power ratios.
Yeah. It's just a simple power ratio. But it's, as I mentioned in the presentation, we're being conservative in the sense that the filter roll-off that we're using in our predictions is much wider and goes into the adjacent channel more than an actual filter might.
Okay. Then we have a two-part question. How does your analysis apply to small cell use in the band? Obviously they're not at 30+ meter height. And will there be a similar analysis for TV white space unlicensed use with the database?
Well, there's an easy one and a hard one.
Let's see what your answer is.
So the simple answer here is, for purposes of the incentive auction, I'll start with part A. No, small cells aren't being considered, but really there's no reason why they couldn't be. It might be more appropriate to model small cells once we have a better idea of how small cells are going to be deployed, either in a typical sense or in a very specific sense. And right now we just don't have that information. So as I said at the beginning of my presentation, the wireless assumptions that we're making for purposes of the incentive auction are based on some typical values that we think are reasonable, but the suggestion is to use those typical values only in the absence of more specific information. So if you have more specific deployment information, whether they're small cells or DAS or whatever, there's no reason why this same methodology couldn't couldn't be used. And what's the other question that I want to avoid?
Yeah, will there be a similar analysis for TV white space unlicensed use with the database?
I don't know. Not a good
No.
answer, my boss says. So there's no proposal to extend this analysis to that case. That's about all I could say. Thank you.
The small cells. So when we start talking about impaired markets, and one of the struggles we have with it, and I think we had a bullet on the slide saying, well, that's all assuming, a classical ubiquitous coverage, antennas at 30 meters and so forth. But there are lots of things you can do to kind of deal with this. So when you talk about impairments, it may not really be a problem if you're using things like small cells that aren't using antennas that are way up in the air. And on the second question, to begin with, in the Commission's proceeding, we certainly proposed to provide spectrum in the guard bands consistent with the statute for unlicensed, and I think that's still one of the things that the agency is looking at as part of the overall picture. But unlicensed is not protected against interference, and what it basically does is designed to work around those sorts of things. So there's performing this kind of analysis is really not appropriate for those.
Are there any other questions from the audience or the internet? I guess being none, well, that concludes our. Oh, wait. Oh.
Is that from Chris?
I just gave him the card.
I'd just add that if you have any questions that you'd like to ask privately, shall I say, for some reason the last slide didn't make it up there, but if you download the presentation, all of our contact information is there.
Okay. Are external filters for TV being considered, such as the 800 megahertz band in the UK? No. No, they're not. Not at this time. So, if there are no further questions, that concludes our presentation on inter-service interference, and we appreciate your attendance. Thank you.